Question 53. A length of copper wire and a 1 meter long silver wire. So I got two pieces of wire here. I'm going to have to show all my work, equation substitution with units, and this is going to get, I'm just going to start writing stuff now. Alright, so I've got copper and silver. What's that, AG? Okay. A length of copper wire and a 1 meter long length of silver wire. So I've got an unknown length of copper wire and my length of silver wire is 1.00 meters long. They have the same cross-sectional area and resistance. So R's are equal and cross-sectional area is equal. And the temperature is 20 degrees, so the temperature doesn't, whatever it affects both of them equally. Calculate the length of the copper wire. Show all work. Oh man, I hate these. Well, let's plug it away at it. Alright, the first thing I'm going to go find this stuff. I was looking around for some formulas and I found this chart that has copper and silver on it and this thing called resistivity. Alright, and I looked up here in the electricity things and resistivity was the Greek letter rho. So I'm going to say the resistivity for copper is, and I'm looking it up and it says 1.72 times 10 to the 8. And now for this it's got the units up here, but I better write them down to get credit for it. So ohms times meters. The resistivity for silver is 1.59 times 10 to the 8 ohm meters. And it's a lower resistance. So now I know the resistivity of these two things. I know the length. I know the resistances are equal and the cross-sectional areas are equal. I don't know what to do. So I go look for a formula, and I find this thing. The resistance is equal to rho L over A. So this is telling me that the resistance is equal to rho L over A. Now the resistance is the same for both of them, so apparently rho L over A for copper is equal to rho L over A for silver. Well, the A's are the same, so whatever number this is, it's going to be the same for both sides, and I'm just going to pretend that the number is equal to 1. So when I divide by 1, that disappears. I like it when things disappear. Resistance is what we're saying, so resistance is there, so rho L times rho L is the same. Well, now I can work because I know rho for copper, I'm looking for L. I know rho for silver, and I know L for silver, so I simply divide the rho for copper into this quantity, and that will give me the length of copper. So I can write the math, length is equal to rho L over mu copper, rho copper. And so I can plug this in and say 1.59, let's move it over, times 10 to the 8 ohm meters times 1 meter. Divide, look at that, I got rid of that too. 1.72 times 10 to the 8 ohm meters. Now let's see, I'll be left with meters, which I'm kind of hoping for because that'll be a unit of length. And I plug it into my calculator, and I'm getting a length equal to 0.92 meters. Now let's think about that. Silver's 1 meter long. Copper's got a higher resistance, so you would need less of it to have the same resistance. So that just makes conceptual sense. And so there's my answer. Good question 54. The diagram below represents a ray of light incident in a plane mirror. Using a protractor and straight edge on the diagram in your answer book, construct the reflected ray from the incident ray shown for a single point. This is the point where you're glad you brought your protractor. Now, if you look at this picture, the picture isn't right. Towards the very end there, it doesn't quite line up. Don't let that scare you. So technically, at this point, I would construct a normal, a perpendicular at that point, and I would measure my angle from the normal, conclude that it was 10, 20, 30, 40, 50, about 55 degrees, and then construct another one over here to match it. So 10, 20, 30, 40, 55 degrees. That may be off your paper just a little bit. And then that would be my reflected ray. Question 55. A periodic wave travels at speed v through medium A. The wave passes with all its energy, yeah, that'll happen, into medium B. The speed of the wave through medium B is slowed to 1/2 of v. In the diagram in your answer booklet, draw the wave as it travels through medium B. Show at least one full wave. And there's a picture we've got to deal with. And this is only worth a point. A lot of work for a point. But let's do this. Well, when the wave hits, a couple of things must be remembered. One, the frequency can't change. If I've got 10 waves per second hitting this material, let's say this is light in air going into glass, 10 waves per second, I have to have the same frequency. I have to have 10 waves per second inside the glass. If I had fewer, that would mean that there was light building up on the outside of the glass. Think about it. 10 waves per second, and inside I only had 7 waves per second. That means 3 waves per second had nowhere to go. That couldn't happen. You have to go clean your windows off at night in order for it to get dark in the room. You certainly can't have more. You can't start with 10 hitting the glass and have 12 or anything. The frequency is a constant. We know that the velocity is equal to frequency times wavelength. So if the velocity is going to be cut in half, frequency can't change, that means the wavelength has to cut in half too. That's the secret to this problem. As the light slows down, the waves get closer together. The distance is less. So I can look at the picture, and I can see I've got 1, 2, 3, 4 blocks from crest to crest. So my wavelength is 4 blocks. Once I get in here, my wavelength can only be 2 blocks. So let's say we, so I've got 1, 2, 3, 4, 1, 2. I got to have a full wave right in here. 1, 2, 3, 4, yep. 1, 2, I got to get a full wave. Now the amplitude is going to be the same. So I've got to go up, and then down, and then up again. So there's the middle point. So 1, and full wave. I could draw another one. There it is.